We're now going to look at the first order partial derivative of a surface function with respect to y. The limit definition of the partial derivative is illustrated here, and basically what we're looking at is two separate output values, range elements, z values, that are determined by these inputs, and when we subtract these two z values, what we get is a change in z. So let's talk about this first partial with respect to y as being the limit of the change in y as those changing y values get smaller and smaller, where our ratio that we're considering is change in z divided by that small change in y. What we will again see is that this change in z divided by change in y is actually going to give us the slope of a secant line on an intersection curve, and the limit of the slope of a secant line is going to be the slope of a tangent line. So let's look at another conceptual drawing in order to be able to understand the meaning of this partial derivative. So here we have a surface function that has two independent variables, and in order to get the partial with respect to y, we're going to consider a constant x value. When we take this surface function and we fix the x coordinate to being a constant x value, what we end up with is a function that then depends only on y, and this is the equation of a two-dimensional plane curve that exists entirely within the plane x is equal to x1, this constant value of x. So let's look at that plane. And that two-dimensional plane curve is the curve of intersection between the surface and the plane x is equal to x sub 1, the plane that is parallel to the yz plane. So let's consider a domain element here in the floor. The x coordinate is going to be x sub 1, this constant x value, because we're in that constant x sub 1 plane. The y coordinate this time is what varies. So this point can go left and right, which means that the y value is the thing that is changing here. And if we're in the floor, the z coordinate is 0. Now let's fly this point up to the curve and look at the point of intersection with the curve. And this ordered triple is going to be x sub 1, the constant x value, the y value, and then the z coordinate is going to be determined when we plug x sub 1 and y into the surface function. The partial derivative of this function with respect to y is equal to the slope of this tangent line. Now let's take a closer look at two ordered pairs that are on the curve of intersection. And to get from one of these ordered pairs to the other, what we're going to need to do is look at a small change in z and compare that to a small change in y. Remember, x is not changing, we're in a constant x plane. If we were to consider the line that is secant to this curve passing through these 2 points, we would see that the slope of that secant line is the change in z over the change in y. By the way, in this drawing, it looks like that quantity would be a negative quantity since the z values are dropping as the y values are getting larger. So this would be a negative quantity over a positive quantity, yielding a negative slope. So if we look at the slope of this secant line and we take the limit of that slope as this change in y gets to 0, what we see is that we end up with the slope of the line that is tangent to that curve, and that is going to be our first partial of the function with respect to y. So again, we see first partial with respect to y is the slope of that tangent line. Now, in order to calculate this first partial, which has several notations that we'll discuss again in a minute, but these are two of the more common, in order to calculate this partial derivative, the only variable that's changing is the y variable, so the x variables are going to be considered constant values during that differentiation. And then we'll differentiate the rest of the surface, but with respect to y. So any x values in this surface function will be differentiated in the same way that constants are differentiated. We've already shown first partial with respect to y with this functional notation. We could also drop the functional notation. We could use the curly d first partial of f with respect to y, or the curly d first partial of z with respect to y. Both of those mean the same thing. We also might see first partial with respect to y and then pull that functional notation onto the front of it. All of these notations are saying the same thing, that we're going to calculate the first derivative of the surface function, treating y as the variable and x as a constant.